What is the importance of set in real analysis? Why do we use set theory in computing the problems of real analysis? In this video, I would be talking about the basic concepts of set, certain definitions, example, and some of the important properties so that we can understand the basic concept of set and we can use this set theory and the symbols and logic in computing and understanding different problems of real analysis. Welcome to the lesson 2 of this freshman course in real analysis. My name is Shaunak and you're watching this video on my channel Physics for Students. The basic target and objective of this video today is to understand set and set theory, some of the symbols and logic so that we can use further into computing the problems and do the complex things easily in real analysis. In my first lesson, I have talked a little bit about what is real analysis and some of the fundamental details. In case that you have missed it, not an issue. I will be doing a quick recap now on the things which we have done in lesson 1. So in lesson 1, first we started with what is real analysis, a development of the set of real numbers that basically starts with natural numbers, then we move to integers, then we move to rational numbers and then to real number. Well, I would like to say that in real number, further we can branch into what is called a complex numbers. Complex numbers, complex planes, these are quite useful in different branches of electronics and especially in computing the problems of quantum physics. However, we are not considered currently with complex analysis, and real analysis would be something which are very much concerned to real numbers, and that is why the name real analysis. What is known for as complex number is a development on the sets of complex numbers, and currently the theorems of real analysis basically rely on the properties of real number system which must be established, and that is basically goal, seeing the axiomatization and the different rules, theorems, lemma and propositions of real analysis. So this was initially what we covered in chapter 2. Also we found to know that what is a statement is also called a proposition. To be a statement, a sentence must be true or a false. For example, the sky is beautiful is not a statement because it is something subjective. Is it raining is not a statement, it's an interrogative. 2x plus 5 equals to 10 again is not a statement because we do not know the value of x. However, if we plug in the value of x, then here it becomes something not equal to 10. Hence, this is a false statement. We also know that there exists a real number x such that x plus 5 equals to 10. And this is a statement. The reason is that if we plug in 2.5, then 10 equals to 10. So this becomes a kind of a valid statement. So we also covered something called connectives. This sign means implies, so it tells it is raining, implies it is pouring. This double arrow signs is if and only if. So for example, ABCD is a parallelogram if and only if AB equals to CD and BC equals to AD. This signs are basically and or. So this is a kind of an example. If P and Q be two statesmen, with the help of this connectives we form two new statements, P and Q and P or Q. This sign is called a negation. That means that basically this shows something negative. So if P denotes a statement, then negative P denotes the negation. That means this is not a statement. These are with further examples we have covered up in lesson 1. I have given the lesson 1 in the I button. If you're interested, please go ahead and click it. And after this connectives, what becomes very important is that now we group the concept of mathematics, and for that we need what is called a set theory. So first let us define quickly what is a set. So if you see that if S be a set or collection of objects and X be a member, it can be any member, say apples, oranges, anything. That is, if X is an object which belongs to S, we write it as this. And we call is something like this. We call it X is an element of S. We call it X is a member of S, and X is X belongs to S. So all of them literally means something else. However, we can also write in a different notation something like this, which indicates that S is a set of objects X for which the statement P of X is involved to be true. Now, if you write something like this, this means that an object of an element or X is not an element of S. Now it is also sometimes possible to describe the set of by listing certain elements. For example, this one S equals to 2, 4, 5, 9. Then we can say that so 4 includes 2, 4, 5, 9 and 4 is or 7 as we call, is not an element of 2, 4, 5, 9. So we can use those symbols easily, as you can see, to make them understand. So if you take obviously S equals 2, 2, 4, 5, 9, then it denotes a set of consisting of 2, 4, 5, 9 only as its elements. I should have mentioned what is called a finite set, but anyway, this is basically what we called as a finite set. Now we can also represent something like this, 1, 2, 3, 4, 5, 6 with certain dots, and these dots actually means and so on, right? So here T is basically consisting of a set of natural numbers. What are the other sets that we are concerned? There's something called a void state set. Now it is found convenient to utilize the notion of a set such that given any object whatsoever, it is not a member of the set. That is to say, no, it does not belongs to the same. Right, so it is denoted by this Greek letter phi, and we call it as void set, empty set, null set, whatever it is the same. For example, we can write something like this: phi equals to a void set, so obviously phi will be equal to x colon x is not equal to x. Now we can also know that there is something which is called a singleton set, that is a set consisting of a single element is called a singleton set. Now here is an example. For example, this one is also an example of a singleton set. So A represents the capital A, and the small alphabet A represents the element of the singleton set. Now here is something very unique, very important. Since a singleton set has only one element in it, it is also called unit set. Single and unit, mostly they are quite similar to each other. So the cardinal number of a single set, obviously the count is 1. The number of subsets of a singleton set is 2, which is the empty set, and the set itself with a single element. So this is a kind of a quick observation. So here you see the number of singleton sets, that is subsets of a given set, is equal to the number of elements in the given set. Say the vowels are given A, I, O, U, has 5 elements in it, and hence the 5 singleton sets would be this one, right, which are the subsets of any given set. Okay, these are some of the quick properties. You can just read it over. So the singleton set has only one element in it. The cardinality of a set is obviously 1. Singleton set has 2 subsets, obviously. Null set is a subset of every singleton set. The 2 subsets of a singleton set are the null set and the singleton set itself, and the power set of a singleton set has a cardinal number of 2. There's nothing, it is just quite obvious, which comes from the definition. You can go through it. Okay, what are equality of sets? Now if S and T are 2 sets, we write equality as this, which indicates that each element of S is an element of T, and each element of T obviously would be an element of S. What is called a subset? So if A and B are 2 sets such that an element of A is as well as an element of B, then we say that A is the subset of B, and we write it this, and A, or equivalently B, is a superset of this. So it's a kind of a sign, this one, the arrow on the, and then the U on this side. So if A is a subset of B, we say that A is contained in B. Obviously, if it's a subset, it should be inside that. So we also sometimes say that A is a superset of B. So if A is a subset of B, there is no element of A which is not as well as an element of B. This is important. If A is a subset of B, there is no element of A which is not as well as an element of B. Sometimes we say that A is a proper subset of B. I mean to say, this is also a definition. So if A is a subset of B without being the same B, let us see an example. For example, 2, 3, 4, 5 is a proper subset of this. 2, 3, 4, 5 would be included along with that extra one, that is the 6. Okay, what is called a universal set? Now this is very important. So in any mathematical discussion, we consider all the sets to be the subsets of a given set. That means everything is basically coming from a universal set. Say for example, we denote it by E, U or X. So while studying, we study the natural numbers, which is capital N. This should be with math be bold, but anyway, is containing basically the universal set. So if you take this one, this is quite a useful point, that universal set is basically a collection of all elements or members of the relative sets known as subsets. And for example, all the stars in Milky Way galaxy is a good example of universal set if we consider all the stars in the Milky Way galaxy. Okay, now when we study numbers in mathematics, then we are interested in a set obviously with natural numbers. The basic set, which is the bigger one, is considered as a universal set, and its subsets are even number, prime numbers, whatever, fractions, and so on. So now let us see with an example how things would be easier. If we take, say, for example, okay, we have got some important properties. So a universal set can be either finite or infinite, obviously, because it is universal. The set of natural numbers is typically example of the infinite universal set, because it goes on. A set of natural 1, 2, 3, this mark is denotes, as I told, and it goes on. Now let us take an example. For example, we take 3 sets A, B, and C, where A equals to 2, 4, 6, B equals to 1, 3, 7, 9, 11, and C equals to 4, 8, and 11. So the question is that we need to find the universal set of all 3 sets A, B, and C. Now all the elements, as you see, of the given sets are contained in the universal set. So the universal set U, if I take it, of A, B, and C would be given by this. That means it will contain everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9 and 11. Sorry, 10 is not there, right? Most of the time we use, so all the elements of the 3 sets present the universal set without repetition. This is a very important point. All the elements in the universal set should be unique. Now we sometimes use, the sets A, B, C are contained in the universal set. So A is a subset of U, B is a subset of U, C is a subset of U. So I mean to say, if we go back to this example, that A, B, and C, when we are taking these sets, then from here this comes A, all these are subset. Now this is a kind of a mathematical description, but we sometimes use this, which is called a Venn diagram, to show the relationship between states. Now Venn diagrams, as you see, are basically the graphical representation of the sets. The universal set is basically rectangle, and its subsets are, the circles which are being shown over there, and this one A would be a subset, right? So there is a confusion which sometimes the students face, that what is union of sets and what is universal set. I mean to say, because these two words are quite common to each other, so I would like to give you a quick understanding of that. So for example, this one, the universal set, is basically the set of all elements or members of all related set. That is universal. Union is basically, the union of sets is one of the set operation. It's basically kind of an operation between two states, where the resultant set contains all the elements belonging to both the initial elements. Universal set can be denoted by U. The union operation between the sets can be denoted by the symbol U, but this symbol is something different, like A union V. But all these things are fine, but it is good that if we can say with an example. So here is a set U, 3 and 5, and A equals to A, B, C, and B equals to E, F, G. Then this one, you see A, B, C, E, F, G, 3, 5. All of them, these are universal set, whereas A union of B is only A, B, C, E, F, G. Why? Because 3 and 5 is not included on those sets, so it won't be a kind of a, I would say, a kind of a union, right? Okay, so the universal set contains the elements from A, B, and U itself, but union of A and B contains elements only from A and from B. So you see, the union actually is taking the elements from A to B, A and B union, but universal set is taking from A, B as well as U. Right. So that is all a quick kind of an understanding about sets. Now we will go with the next video with the mathematics of the sets. So let us see what we can summarize. We understood what is real analysis with a quick recap. We understood what are sets, what are the different type of sets, what are the important properties of sets, and we cleared up the confusion between universal set and union of set. So our next topic for the next video would be operations of sets on sets, and it will take some time because there are a lot of algebraic operations and others. We will divide it slowly into small videos. Thank you for watching this video. I would be delightful if you can please subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. I am also available in this email ID, which you can contact me, and I have got an exclusive channel on general theory of relativity, which is this one. Further, you can follow me on my Facebook, Instagram, and LinkedIn pages. I hope this series is going good. I need your comments to encourage me more. However, I will be continuing with this real analysis series, and will be continue what is shown in the next video. Till then, goodbye.